All right, so and today I'm going to talk about DAGs, BFTs, and where they meet. This is based on a joint work with my co-authors, George, Neil, Edith, Lefteris, Oded, and Alberto. We all been at Novi at some point, and now we're all at different places, but the entire work started at Novi. So the last 2 years, we worked on DAG and the DAG approach, and we had a lot of fun, and now spread in 2 different papers. We published All You Need, the DAG and PODC, where we established the theory, how you can have a DAG and run a consensus on top of it with like optimal amortized complexity, post-quantum security, and all the one latency. Then we published at EuroSys the Narwhal system, where we actually demonstrate how can you build this DAG very, very scalable in a very scalable and efficient way. And Bullshark is our upcoming paper in CCS 2022, where we show the fast path, garbage collection fairness, and trivial chain quality. So I don't think I need a lot of introduction in this audience into what consensus is, so I would just dive into the details. When I say DAG, I mean, at least in our approach, we mean the round-based DAG that is post-proposed by Aleph in AFT 19. And here we have validators, we have rounds. In each round, a validator can propose 1 node per round per validator. And it's structured because every node has to refer to at least n-f nodes from the previous round. So this is how it's structured. This is the DAG. And what else is important here? Nothing. This is the DAG, and I'm gonna yeah, nothing. Very simple. I'm gonna explain in this talk Narwhal, which is the system, as I told you, how we build this DAG very, very efficiently. And the other part of we have Narwhal building the DAG, and on top of it we have DAG-Rider, Tusk, and Bullshark, which are all protocols to look at this DAG. This is a DAG. They all have a their own view of the DAG. And then they can just totally alter everything, get the ledger, totally alter everything with, and the important and cool thing is that there is no communication, no communication. They just look at their local copy of the DAG and alter it. Nothing more they need to do. So we actually abstract all the network layer into building the DAG, and then we get consensus just locally for free. Not for free, we need to run some computation, but it's very, very simple. Okay, so I cannot talk about all these works in 25 minutes, so I decided to, actually it's going to be tough to do it in 25 minutes, but I think the standard here is kind of flexible, so I... So, okay, let me try, I will try. So in Bullshark, we have 2 variants. We have the full Bullshark, where we have the fast path, and then we have the asynchronous fallback. And we found the fast path is so cool, it's so simple. So we must have like a standalone partial synchronous Bullshark protocol. And this is what I'm going to present here. So as I said, I'm going to say how we build the DAG shortly. But for now, just assume that we just use reliable broadcast to broadcast the nodes. Now, to broadcast the nodes in round 2, I need to wait to get n-f nodes in round 1. Then I prepare my node, I put my transaction inside, I add the links, and they just reliably broadcast it. And what it gives us is 2 important things. Now, first, it's asynchronous, right? Reliable broadcast just eventually guarantee that we all deliver the same nodes. But in any given time, it's possible that validator 4, for example, will have a node that validator 1 does not have yet, right? However, the non-equivocation property given by the reliable broadcast says that if they both deliver the same node, the same round, the same validator, it has to be the same node, the same transaction, everything has to be the same references, the same transactions, and by applying the same logic like recursively, and if we look at the causal history of these nodes in these 2 different local views, they have exactly the same causal histories, and this will be important to like order everything. Okay, so with that in mind, I'm going to jump into the details how we interpret the DAG. So we look at the ages of the DAG, these links as votes, you can say, and this is how it works. So we divide the DAG into odds and even rounds. In each, depends how you start counting, but let's say in each odd round we have an anchor. You can call it leader, it doesn't matter. I just think the anchor is a better name here. And then the even round, in the even round we have the votes. And we say that a node votes to an anchor if we have a link. Okay, so, and the goal will be the following. So first we will need to agree what anchors we are going to commit. And then we are going to go and one by one order their entire, deterministically order their entire causal histories. And I will explain, it will become clear. Okay, so let's talk about the commit rule, which is extremely simple. The commit rule just says that if you see f+1 votes, you can commit. So in this example, this is the local view of validator 1. So validator 1, in his local view of the DAG, he sees there is one vote for A1, right? You see one node in the second round, which link to A1, to the first anchor. And so we cannot commit it. Doesn't satisfy the commit rule. However, if we check the second anchor, we have 3 votes and it can commit it. Now remember, each validator can have a slightly different view of the DAG. So it's possible in this example that validator 4 already deliver a node, you see round 2 validator 4, that validator 1 doesn't see yet in his local view of the DAG. And therefore, the commit rule for A1 is satisfied in the local view of 4. Validator 4 committed A1 because it sees 2 votes, f+1, f is 1 in this example. So we need to make sure that when validator 1 order his anchors, he goes and order A1 before A2. Now, of course, probably the only trick we know in distributed in this blockchain is quorum intersection. And of course, we are going to use it as well here. So I told you before that we need f+1 votes required to a commit, and each node refers to n-f nodes from the previous round. So together we get that like a simple observation that I will explain in the example in a second, but if an anchor A is committed, then all future anchors will have a path to at least one vote for A, and thus will have a path to A itself. So here is our simple example. So validator 4 committed A1, right, 2 votes. Now A2, we said every node in the DAG has to refer to n-f nodes. So now we still see 2, right? We need another one. So it doesn't matter which one he picks, it will refer to a vote, right? This is a quorum intersection. And thus there will be guaranteed, if A1 is committed, there will be guaranteed a path from A2 to A1. And with this observation in mind, what if we look at the opposite logic, what we know is that if there is no path from a future anchor A prime to A, then it's impossible that any honest validator committed A. Okay, so now we're ready, and in one slide, I'm going to present you the entire partial synchronous Bullshark protocol. Okay, so this is how, let's say validator 1 sees the DAG. This is his local view of the DAG. So he cannot commit A1, he only sees one vote. So the commit rule is not satisfied. He cannot commit A2, he doesn't even see A2, right? So 0 votes. However, A3 is good. He has 3 votes for A3, he can commit A3. Now he needs to go back and check whether he needs to order A2 before A3, right? So the way we do it is very simple. If there is a path if there would a path between A3 to A2, he would order A2 before A3. However, there is no path, which means, by the observation from the previous slides, that no honest validator committed it, and it's safe to just skip it. Now we continue this protocol, and we check if there is a path from A3 to A1. There is a path from A3 to A1. So A1 is ordered before A3. And now here it's important to know that if there is a path, it means that A1 might be committed. It's not 100% guaranteed that it was committed, but it doesn't matter. Because I told you before, if we all see A3, like when we, in our local views, deterministically apply this rule to order the DAG, we agree on the causal history. We're saying the same causal history. So we'll apply the same deterministic order. So if one decides to order A1 before A3, the rest will decide to order A1 before A3 regardless. And so this is safe. And now, after we ordered the anchors, okay, one important thing is that we continue recursively. When we order A1 before A3, now we continue recursively from A1, and this example A1 is round 1, there is nothing before it, but if it wasn't round 1, so we continue this applying the same logic. We will try to see, is there a path to A0? Yes, we take A0. No, we continue is there a path to A-1? And we continue recursively until we reach an anchor that was previously ordered. Okay, so we finished ordering the anchors, and now what we do is very simple. We just go these anchors one by one and order their entire causal history. So in this case, A1 doesn't have causal history. This is the first round, but we can order the causal history. We can order the causal history of A3, just applying some deterministic rule. And again, because if 2 validators see A3, they see the same causal history. They will apply deterministic rule. They will agree on the order. Okay, cool. So this was the entire protocol. Now let's talk a little bit about properties. So chain quality we get for free. Because of the structure of the DAG, it is guaranteed. We need n minus f, which is 2f plus 1 nodes in each round. So out of which at most f can be Byzantine. So we have at least f plus 1 out of 2f plus 1 honest, which is more than half of the nodes in the DAG are guaranteed to be on the total order is guaranteed to be generated by honest validators, and it's actually proven to be optimal. Now, another two important properties that we need in blockchains, I think, is fairness and garbage collections. Now, fairness is not in the fairness that it's a kind of different fairness. What I mean by fairness here is that we have this pool node in Australia, right? We keep talking about him. He's slow, nobody waits for him. He's not able to ever like put his own transaction in the ledger. So we want to be fair to him. And even if he's slow and he's not fast enough, so validators were fair to him, because he always came late, these broadcasts always came late, we still want to be able to order it. So we introduced wink links. So and just when we build our node, we still refer to n minus f from the previous round, but we also refer to nodes from previous round, just so they will be part of the causal history that we will later order. However, if you want to garbage collect, and we do want to garbage collect because this is very important in practice, it's easy to see that we cannot achieve both fairness and garbage collection in asynchronous periods. So what we do here is that we decided to provide garbage collection no matter what, synchrony or asynchrony, and fairness we provided during the synchronous periods of the network. So if this node from Australia is fast enough to broadcast this node in a window, say, of 10 rounds, it will be fine. We will link to it and it will be fine. Otherwise, we will garbage collect. So the garbage collect is, this slide is a bit too much information. I'll not go through it, but I just say that it's really not a rocket science. Once we have the round-based DAG structure, together with consensus, it becomes very easy because because we have consensus, so we are gonna order the causal history of this anchor A at some point. Then we are gonna just assign times based on the median of the times in each round to nodes in the round. And then we'll just decide everything below some delta distance from the timestamp of A, we are going to garbage collect. So the round structure together with consensus makes it very, very simple. And I don't want to spend more time on that, but you can check the paper. And okay, so just to conclude, Bullshark is an extremely simple protocol. As I show you, there is no complex view change mechanism, no view synchronization, nothing of this kind. Just one type of message, then you check the DAG locally and you just order everything. It's leaderless, so we have perfect load balancing and network utilization when we actually build it. We have chain quality for free. We get fairness during synchronous period, and we can easily garbage collect it. And this is quite important because the only works on DAGs, they had this problem of garbage collection, which wasn't clear how to garbage collect them. So, okay. So this will conclude the presentation. I do owe you something. I want to talk a little bit about the liveness of the protocol, but before that, I want to briefly describe what Narwhal is, because I will need it for the liveness description. So as I said, Narwhal is actually the system, how we actually build this DAG. So I don't think I have too much time. So I will just say that the current design, if you look at the current design, the current protocols like Tendermint, Hotstuff, SBFT, they're all monolithic in the sense that they share transaction data as part of the consensus. And then they optimize the overall message complexity of the consensus protocol. So now from a theory point of view, this is a very nice, very cool problem, nice problem. I worked on it myself. This is really, very interesting. However, when you really implement the system, you realize that this leader sending to everybody, collecting for everybody, sending the data to everybody, collecting signatures, sending the data again. If you check the resource utilization, you see that the leader is always overwhelmed. It's always the bottleneck, while the rest are just doing like really nothing, just verifying one signature, sign something, and send really. So, and of course, the leader is the bottleneck, and the whole system cannot perform better than one leader. So with this, the key observation that we had in Narwhal is that if you want to build efficient and scalable Byzantine systems, Byzantine consensus system, you need to decouple data dissemination from the metadata ordering. So when we build the DAG, we are not putting the data on the DAG. The data contains on the metadata. In our case, it's a proof of availability. In high level, what we do is that we stream the transactions to the validators. They return to us signature that they have the transaction. We form a proof of availability, which means if I give you a proof of availability, it's guaranteed that even if you locally don't have the data, you see that enough people signed it, enough people have the data, enough validators, so you will be able to retrieve the data later. So it's safe just to put the proof of availability on the DAG and not worry about the data. You can worry about the data later only if you don't have it. In the common case, in the optimistic case, we'll all have the data always. Okay, so just in brief, Narwhal is a scale-out architecture. We have workers and primary. We have one primary, many workers. Now, each worker can be a process on one machine, or if you want to use cluster, you can use the work like separate machine per worker and scale out your performance. And the workers get transactions. They keep streaming them. That's the important part. Just keep streaming the data, non-stop. The workers stream the data. Then they pass the digest of the data to the primary, and the primary all the primaries together, building the DAG using only the metadata. So the protocol that they are using is some sort of a consistent broadcast. Not very, I don't know how much time I have, but really, really briefly, they just, I have 7 minutes, is a lot, I can start over, yeah. Okay, so they send the primary send the headers contain the reference to the previous nodes in the DAG, and the digest. When a validator gets that header, makes sure we have the data, he signed that they have the data, return, and then the primary collected to a certificate. This is the proof of availability, sends it again, and this is around in the DAG. This is how to build the DAG, and then the actual DAG is just this proof of availability, is the certificates. Okay, now a few words about liveness. So if as I told you, there is two ways to interpret the DAG. There is against an asynchronous adversary and against a partially synchronous adversary. And of course, for the asynchronous adversary, we have to use randomness. Otherwise, we have FLP result, right? So the way we do it is that we use a future round. We add some threshold signature shares into the DAG, and we use a future round to compute the randomness that we will and elect in retrospect unpredictably a leader. Now, if you're familiar with WABA, that's basically the same trick. First, we let the adversary to commit to some schedule, to commit the structure of the DAG, we apply some simple combinatorial argument that shows that at least two-thirds of the nodes will satisfy the commit rule. And then we unpredictably elect the anchor, the leader, and with probability 2/3, we were able to commit this. We call it wave, and this is a known technique. And now this is for the asynchronous liveness. Now for the partially synchronous liveness, again there is no magic. Like it's a deterministic protocol. We have to use timeouts. And we also we don't have randomness, so we need to predefine these anchors. Now the way to use timeouts, we actually consider two alternatives. So one way is to say I'm going to use timeouts on the DAG structure itself when I build the DAG, which means that before I told you that in order to add a node, I need to wait to n-f nodes from the previous round. Now I'm adding to this. If I have the anchor, the predefined anchor leader in this n-f, I'm good, I can move forward. Otherwise, I will wait until a timeout to get it. If I don't get it, I don't get it. If I get it, I get it. But I will wait for timeout to wait for it. So this is one approach, it works. And this is actually what we did. But the other approach is, okay, say I wanna continue building the DAG as fast as possible. I don't wanna wait. N-f, I continue, new round, right? Say I wanna do that. So what we did, we tried. What we tried is that we separate the physical layer of the DAG, how we build the DAG, from a logical layer of the DAG. So once in a while, I can add a bit and say, okay, this now I'm ready. This node is actually part of the logical DAG that on top of which I'm gonna run Bullshark, right? So and it also works, and we compare the two approaches, and it turns out that the first approach is actually much better in practice. And this was surprising for me because I thought, for sure, like I want to move as fast as possible with building the DAG, right? But this kind of things that only after you build the system in retrospect you get the intuition you didn't have before. And the reason is because, as I told you before, we are streaming the data. So the DAG is only metadata. So if we are slower on building the DAG, it only says that each node will contain slightly more metadata, slightly more proof of work. The entire data behind it will be the same because we keep streaming it no matter what, right? But on the other hand, if our DAGs are bigger, it's more networking, more bandwidth, more threads, much bigger data structure that we need to handle in memory. Garbage collection becomes more difficult. So So we ended up doing the first approach, which were more performant. 3 minutes, good. Just on time. So in terms of implementation, everything is written in Rust. We used real networking, real storage, real cryptography. Everything is open sourced under Alberto's GitHub. And for the experiment, we used a Geo replicated AWS. It was really, really, really expensive. But Novi paid for everything, so we're fine. And okay, and here is the latent throughput graph. So in red, we see the vanilla, we compare to hot stuff. So in red, we see the vanilla hot stuff without decoupling data from metadata. Then we have our own implementation of hot stuff where we actually compare, we actually decouple data from metadata. You already see it's already much better. So the idea of decoupling the data of the metadata works. And then you also see the Bullshark in blue and green is the Tusk protocol. And the Bullshark is a bit, is better latency, where the Tusk has slightly better throughput. Here is the fault, performance under faults. So 1 fault, 3 faults. And you see that the hot stuff suffers even if we decouple data from the metadata, while Tusk and Bullshark are still performing very well. And okay, and with this, I want to conclude the talk. So the papers are available online. If you want to read some more extended summary of it, of all this work, you can check my blog post under Decentralized Thoughts. Any questions, everything, you can always reach out. We are in Aptos Labs really happy to collaborate. And as you can see, I'm wearing the painter uniform. If you're asking yourself, what is this? This is because we are painting the future of Web3. So, and we are hiring, by the way. Yeah. And okay, and thank you so much. I'm happy to take questions.